we need to predict the product given these two reagents and this compound. Looking at this compound, I see the hydroxyl group has to be the leaving group. However, it's a very bad leaving group. However, we have a TSCl and pyridine that react to create this OTS, the tosylic group, which is a good leaving group. And for our second reagent, you see here, the DBU is a very good base. So I can draw a pair of electrons with minus charge. However, it is a very bad nucleophile. Therefore, this reaction favors the E2 reaction. And if alpha carbon bears the leaving group, the beta carbon is one next to it, and in the elimination reaction, the proton is abstracted on the beta carbon. And looking at the top here, I know that the hydrogen must be in dash that correspond with our stereochemistry, and the hydrogen on the bottom need to be in wedge. If I want to draw this mechanism, I may be at a loss which hydrogen to abstract. The E2 reaction favors anti-periplanarity. Long story short, this happens with the anti-parallel position of the leaving group and the beta proton in the Newman projection. See, it's about 180 degrees. And looking at our stereochemistry of the leaving group and the beta proton, I see that the upper hydrogen and the OTS, the tosylic group, are both roughly below the page, so they will never make the anti-periplanarity. However, on the bottom hydrogen with the tosylic group, the hydrogen is popping out of our page or screen, and the the OTS is going below our screen. So therefore, you can see that that will match up to be the anti-periplanarity. And now I'm gonna show you the electron arrow mechanism where this DBU has a proton transfer, meaning abstract the hydrogen, and we form a double bond specifically between the two carbons, and then that in turn creates the leaving group to leave our compound. And in the end, our final product looks like this. However, you need to have the double bond right here. And because we have sp2 hybridization, it takes the plane geometry. So instead of having a dash, I have to have a just plain line extended with CO2CH3 connected as a substituent. And on the top here, I'm gonna preserve the stereochemistry, and that's our final answer. Now, in case you draw this in chair conformation, I just wanna warn you that you are not getting the transformation. So, for example, I can draw the chair like this, and whoa, what is that? Okay, it's not a good looking, but notice that we cannot have a double bond in the trans because that's going to create a lot of strain according to the Brad's rule. So trans is not observed any ring carbons that has 8 members. So this is not what we see. Instead, this hexagon you see must be looking something like this. Okay, here you can have double bond like this to form the cis, and energetically that's more favored than the trans.